All right, guys. Today we're going to do another lecture. We've got on 2.1. Normally I don't do lectures on the definition sections in the chapter, but this is entirely possible. It might be that this is most people's first exposure to what's called linear algebra or matrix algebra. And so I wanted to actually go over the definitions. As such, there are no prerequisites for this particular section because, again, I'm just going to be going over what things are called so that you guys will be aware when I use terminology, what I'm referring to with that terminology. So let's just go ahead and get in it here. We've got matrix definitions. The first thing is, well, what's a matrix, right? The intuitive definition is a matrix is just a grid of numbers. It's an array of numbers. Now, we typically label them with capital letters. So let's just call this one A. Okay. We use square brackets here. Okay. So it's giant square brackets, and it's got some numbers in it. So maybe like a 1, there's a 2, maybe a -5. I don't know. Maybe this one's a 1/2, a 0, and maybe a 4. I don't know. Okay. They don't have to be whole numbers or just rational. Any numbers in here. This is a matrix, and we call this matrix A. Okay. So a few things about A. We call individual entries here. So let's say this one. Okay. So these are the elements. Okay, so those are the elements. These horizontals obviously are called rows, but specifically these are row vectors. Okay, so this is the first row vector, the second row vector, and these of course would then be the column vectors. Okay, the column vectors of A, right? So if I say first row, this is the first row, second row. If I say first column, second column, third column, and those are my elements. Okay. I need to be able to refer to the elements in a very, very specific manner, though. Notice how I can say first row, second row, first column, second column, third column. But how would I specifically refer to this entry? If I didn't know it was a 4, what if there's more than one 4 in my matrix? How would I refer to that? So what we do is we use what's called an indexed notation. Okay, so I'm going to erase the actual numbers in here, and I'm going to put in the notation that we typically use. Okay. All right. So what we do is we look at any given entry, and we look at the row and the column that entry is in. So for example, this first entry here, this entry, I'm going to use a lowercase a. This entry is in row 1 and column 1, and so we're going to call this entry A11. The first index is for the row, the second is for the column. So that's row 1, column 1. And if you're following along, the one to the right of this would be what? Well, let's see. So it would be row 1, but now we're in column 2, right? So that's A12. And the one to the right of that, still row 1, but we're in column 3 now, so A13. Okay? If I move just below A11, this is now row 2, right? But it's row 2 and it's column 1, so A21. Here we have row 2, column 2, and finally row 2, column 3. So using this particular indexing strategy, now I have a very specific name for every location in my matrix. Okay, you may see an arbitrary matrix labeled in the following form. We'll call it okay. So this just means that I have A, and I'm referring to it as a collection of A sub ij. The A sub ij are the elements where I is the row location and J is the column notation. This is commonly referred to as referring to the matrix in index notation, and a lot of the definitions we're going to get are going to be defined via index notation definitions. There's going to be an intuitive definition that's natural to think about, and I'm okay if you think about those. But we're going to do some proofs later on, and for the proofs, you're going to need the index definition. So I'm going to give you those when they come up. There will be a couple of them in the lecture today. But again, try to keep those things straight, right? If you ever see an index notation, one of the best things you can do is just make an example and just see if you can puzzle out what the natural appearances from there. So in this case, the one thing I do note is that A, whenever I write it, has a fixed number of rows and columns. Okay, this particular one has 2 rows and 3 columns. Okay, so here we go. I've got, that's 2 rows, 3 columns. And in this case, what we would say is that A is a 2 by 3 matrix. Okay, so it's the number of rows and then the number of columns, 2 by 3. We also may write it this way. So this is equivalent to writing, or we put A and then down here we put 2 by 3, right? So that's A is a 2 by 3 matrix. Okay. All matrices are going to be rectangular, right? We're always going to fill it out. You're never going to have some random elements missing. Okay. They'll all be rectangular, but in the very nice case where the number of rows happens to be the same as the number of columns, I'm pretty sure you can anticipate what we're going to call those. But if the number of rows and columns are the same, we call those square matrices, right? Yes. So the formal definition would be A, which is an M by N matrix, is square if M equals N, right? So if it has the same number of rows and columns. And that makes sense, right? Because it's going to make a damn square, right? It's perfectly reasonable. Okay, so let's talk about some other definitions. I need my eraser here. Some other definitions. Okay, so we've got the size. These are also sometimes called the dimensions, right? But in the same way as 2 feet by 3 feet, etc. So let's talk about specific types of matrices, right? Let's talk about specific types of matrices. Okay. If I consider a matrix, and I'm just going to put just the general notation here. If I consider a matrix with index form, okay. What if I define something? So what does the following type of matrix look like? And if I want you, after I give you this, I want you to sort of pause the video and I want you to try to think about what this might look like and maybe draw something. So what do I say? So I'm going to give you a definition in a second. So I'm going to say A is, I'll fill in this number, this word in a minute. If A sub ij equals 0, so this is referring to individual elements, right? So specific elements are going to equal 0 when, I'm going to give you a condition, when I is less than j. Okay? So what I'm saying here is, suppose I have a matrix where the row index is less than the column index, right? Okay? And for every time the row index is less than the column index, those values are all 0. Okay, well, what would that look like? Well, I don't know. Let's see if we can make one, right? I'm just going to make an arbitrary example here, right? So let me make a matrix. I'm going to say this is 3 by 3. We're going to see if we can't fill it in, right? So let's find all the entries where I is less than j. So this first one, this is the 1, 1 entry, right? So I don't know what that is because this doesn't tell me, right? This just tells me it's 0 if the row is less than the column, but it doesn't tell me anything else. So I don't know what that is, right? But how about this one? This is the 1, 2 entry. That's got to be a 0, right? Because for A1, 2, right, since 1 is less than 2, the row is less than the column, that one has to be 0 by this definition. Okay? Well, this is A1, 3, and it's got to be 0 for the same reason, right? Okay, this one is A2, 1, but I don't know anything about that one. This is A2, 2, don't know anything about that one. This one's A2, 3, And just like 1, 2 and 1, 3, 2, 3, the row index is less than the column index. That one has to be 0. This is A3, 1, don't know anything. 3, 2, don't know anything. And 3, 3. And what has happened? Okay. Well, what we notice is actually all of these entries where the row is less than the column, the row index less than the column index, they're all located in the same spot in my matrix, right? They're all located above this region here, which we call the diagonal. Okay? So this is the diagonal. Now, I'm not going to write out the formal definition, but I'm sure you could probably come up with one. Look at the entries on the diagonal. A11, A22, A33. If we kept going, it would be what? 4, 4, 5, 5. The diagonal is just the ones where the row and the column have the same index, right? This type of matrix right here is called lower triangular. Note that everything that's not in the lower triangle, see, lower triangle, has to be 0, right? So this is a lower triangular matrix because I only have non-zero data, I only have useful data in the lower triangle. And you can imagine, of course, we're going to have an upper triangular definition as well. It's exactly analogous, okay? So we're going to go ahead and say A is upper triangular. We'll abbreviate these to LT and UT later on, okay? So it's upper triangular. Similar definition. If A sub ij is equal to 0 when, well, let's look at it. If it's upper triangular, I want the stuff below the diagonal. I want these to be 0. And let's look at these. That's 2, 1, 3, 1, and 3, 2. And for all of those, the row index is bigger than the column index, right? So it's upper triangular. So this is what I was talking about when I said there's a difference between an intuitive definition and the formal index definition, right? So the intuitive definition for lower triangular is, well, I have stuff in my lower triangle and everything else is 0. That makes sense, right? Upper triangular, same thing. But for the proofs we do later on the semester, you're going to need these index definitions, right? So again, keep these in mind. I'll never ask you for a specific definition, but you may need them later on, okay? I can combine these two as a sort of a thought exercise. Can a matrix be both lower and upper triangular at the same time? Well, in order for that to happen, it would have to fit both definitions, right? Well, let's see, what would that look like? Well, if it fit both definitions, then everything in the upper triangle would have to be 0. And everything in the lower triangle would also have to be 0, right? In fact, the only things that don't have to be 0 are the ones on that diagonal right there. So what do you think we would call a matrix that only has non-zero values along its diagonal? I bet 90% of you just said a diagonal matrix. Yes, and in general, I should just point this out, mathematicians tended to name things exactly what they look like. Yes, we have to spend our brain power doing other things. Giving things clever names is not one of them, right? So that's a diagonal matrix, okay? There is a very random thing that's not going to come up very often, something that we call the trace. This will have a somewhat unrelated definition, but it is related to the diagonal. The trace of A, okay? So this is also notated TR of A, so the trace of A. This is the sum of all A sub ij where I is equal to j. So this is literally just the sum of all the diagonal values, okay? So if for some reason you wanted to look at your matrix and you wanted to add up all the diagonal values, that gives you a number. That's called the trace of A, okay? Again, not going to come up very often, but it's in the definition section, so I figure why not. Okay. All right. So let's get to the first. Actual. I just lost my eraser. I swear. Let's get to the first actual operation that we have for matrices. Things that you can do with them. Right. It's always fun whenever you learn new numbers. That you learn what to do with the new objects. Okay. So I'm going to get a real example up here. I'll give you the formal definition for this in a second, but I want to show you what it is first. Okay. So let's get I want to make A 2 by 3. I'm going to do a lazy matrix. We got 1, 2, 3, 4, 5, 6. There we go. Okay, fantastic. So there's a matrix. Okay. So I want to introduce an operation called a transpose. Okay, so a transpose. So I've got A transpose, right? And again, the notation for this actually is you put a t in an exponent. Now there's a reason we put the transpose as it looks like an exponent. We're going to have to track order of operations at some point, right? And by putting the transpose here, I'm writing when this should be done, right? So this should be done at this whenever the step you would do exponents would be done. So what the hell does the transpose do? Well, let me give you the intuitive version first. The intuitive version is the transpose swaps the columns and the rows. So let me work this one out here. So A transpose. So what's going to happen is the first row will become the first column. Okay? So row 1 is 1, 2, 3. For the transpose, column 1 is 1, 2, 3. Okay? For the original matrix, row 2 is 4, 5, 6. For the transpose, second column, 4, 5, 6. Okay? Now note, transpose does not maintain the size or the dimensions. It doesn't preserve size. I started with a 2 by 3 matrix and I ended with a 3 by 2 matrix, and that is a big deal. Okay? It's a very big deal. These two matrices, A and A transpose, they can't even be added together. And if you can't do something as simple as addition with two things, then you've got to be very careful on how you're designing your algebra here. So again, this one's 2 by 3, and this one's 3 by 2. Now that's it. There's no exceptions, no tricks, no gimmicks, right? You literally just swap the columns and the rows. Okay. The formal definition is honestly, the formal definition is very simple. Okay. A transpose is just the collection A sub Ji. Yeah, all the transpose actually does is it swaps the indices, right? This was entry 1, 2, right? That would be row 1, column 2. If I swap the indices, right? So instead of it being 1, 2, it would be 2, 1. That's where this element goes. This element goes to the 2, 1 position. Row 2, column 1. That's it, right? This is the 1, 3. It goes to the 3, 1 position, right? This is the 2, 2. It goes to the 2, 2 position. Note that the 1 and the 5 didn't actually move. Still in the 1, 1, still in the 2, 2. The diagonal doesn't actually move. So all the transpose does is it swaps the indices. Okay? All right, fine. It's reasonable. Okay? Okay, so some definitions involving transpose. Okay? It is possible that you have a matrix. So let's say, suppose A equals A transpose. What if a matrix was equal to its own transpose? right? So you take the transpose. I know some of the elements don't move, but it's possible that the elements I do move just end up in the same spot as, well, an element of equivalent value. Okay? So is that possible? Sure. Well, what would we call this? Okay? We say then A is symmetric. Okay? A is a symmetric matrix. Okay? Formal definition is pretty easy. Okay? The formal definition, I'm going to put it in a different color because I'm not going to write the first part of this. Okay? So A equals A transpose if A sub ij equals A sub ji. This symbol means for every. So for every I and j. Okay? So every possible pair of indices, they're just equivalent. I encourage you right now, pause the video and see if you can't actually write down a non-trivial 3 by 3 matrix. And by I say non-trivial, I mean don't put zeros everywhere, don't put ones everywhere. It's ridiculous, right? Yeah. Make a non-trivial 3 by 3 matrix. Go ahead and pause the video now. Okay. All right. Hopefully you were able to do it. I'm going to write one up here just because. Okay. It's a pretty easy way to argue through this. And I'm not actually going to put numbers in here. I'm going to put letters, and we'll just follow along. So what can I put in the 1, 1 position? Well, I can put anything I want, right? The only requirement is that it's got to be the same in the original as the transpose. Well, yeah, but under transpose, the diagonal doesn't move, right? So you can put anything you want there. Those elements aren't going to move, so it doesn't matter. So my diagonal here, I've got A, I've got B, I've got C. I don't know what those values are. They can be anything I want. Now, let's look at the 1, 2 entry. The 1, 2 entry, again, I can make that whatever I want. However, once I make the 1, 2 entry, let's say D, well, it's got to be the same as if I took the transpose. And when I take a transpose, the 1, 2 element is going to move to the 2, 1 position. So this one also has to be D, right? Those have to be the same so that when I take a transpose, the values won't change. Sure. Same thing for this one. The 1, 3 position has to match the 3, 1 position, and the 2, 3 position has to match the 3, 2 position. Okay? That's it. So everything of this form, okay, everything of this form would end up being a symmetric matrix. Fill in whatever numbers you want for A, B, C, D, E, and F, right? Okay. Now, one of the things that I'm going to want you guys to sort of think about later on in the semester is the concept of degrees of freedom. It's the concept of when you're trying to create something, how many choices do you get to freely make? Yes? For any 3 by 3 matrix, it seems like you get to make 9 choices, yes? Just a random 3 by 3 matrix, you get 9 choices for what to put those numbers in there, right? There's 9 entries, pick whatever you want. But when you start putting rules on it, when you start restricting what you're looking at or what you're looking for to a specific type of matrix, like a symmetric matrix, you start to lose some of that freedom, right? Take again, this is an arbitrary symmetric matrix. How many degrees of freedom do I have here, right? How many free choices? Well, it looks like I've got 6, not 9, right? I can pick anything I want for A, for B, for C, for D, but once I choose D, that choice is taken from me, right? If I put a 7 here, well, a 7's automatically got to go here. If I put a 9 here, a 9 automatically has to go here, right? So instead of getting the full 9 choices, I only get 6 of them, right? This is going to be really crucial for us to know the size of our solution spaces later on when we start doing some other problems, right? Almost everything this semester is going to have infinitely many solutions, right? So you're going to need to be able to write those in some form that allows you to characterize an infinite not an infinite dimensional, but an infinite space with finite dimensions. Okay, so one more. Okay, this is if A is equal to A transpose. We call it symmetric. What if A is equal to negative A transpose? Now, I know we didn't cover what negative means, but negative matrix just means turn all the elements negative, right? Or at least swap their sign. I want you to pause the video and see if you can't come up with a 3x3 skew symmetric matrix. This is harder. A good bit harder than the other one, unless you think about it real well. Go ahead and do that now. Okay, so let's see, skew symmetric. That's what this is called, skew symmetric. How do I make a skew symmetric matrix? Well, maybe it'll help if I write down my definition, my index definition. So I've got A is equal to negative A transpose, and the only way I can do that is if A sub ij is equal to, and I'm actually going to write it down, negative 1 times A sub ji for every I and j, right? Now that's actually really interesting, right? So I'm going to see if we can't write one. And as normal, I'm not going to put numbers. I'm going to try to make this as general as possible. Let me see if I can't write down a 3x3 skew symmetric matrix. I want to focus on two different types of elements. What about the diagonals, right? So what about the diagonals? So the diagonal, A11, when you swap the indices, it's still A11, right? Yeah? So Aij equals Aji in that particular context. So, but what does that mean? If the indices don't actually change because they're the same, they're on the diagonal, then the number would have to be equal to itself times negative 1. How many numbers are equal to themselves times negative 1? How many numbers are their own additive inverse? Well, just one, right? 0. The diagonal entries all have to be 0. Because when I take the transpose, they won't move. Then I'm going to multiply them by negative 1, and they can't change. Because they got to be still equal to their original value. Yeah? So already I know every skew symmetric matrix, diagonals are all 0. Okay, fine. What about A12? So these are non-diagonal entries. Well, A12, I don't know what that is. Could be anything. But once I pick a value for A12, I know what the value for A21 would have to be, right? It would have to be the opposite of this value, negative A. Right? Again, I lost a choice, right? If A13 is B, then 3,1 has to be negative B. And if 2,3 is C, then 3,2 has to be negative C. Okay? And these are all of your 3x3 skew symmetric matrices, right? They got to look just like this. Okay? Now think about it for a second. How many free choices did we get? Which is 3 this time, right? I put a larger restriction on my objects and I lost some of my free choices, right? My arbitrary matrices, just any 3x3 matrix, I had 9 free choices. Now, I've got 3. Okay? Okay, fair enough. We'll do something more with that idea of having free choices eventually in the class. For right now, I'm gonna leave it there. Just when you're working with these things, sort of try to keep that in mind. Okay. And I've got one more thing here. One more definition. And this is another one of those things where you can read it and pretty much know exactly what it's supposed to be. We've got a matrix function. What is a matrix function? Well, it's a matrix with functions in it. That's it. It's It's not complicated, right? So we've got, let's say A, I'm going to make this one 2 by 2, and let's say you've got x squared sine of x hyperbolic tangent 5, right? That's a matrix function, right? So a matrix function is, again, it's just a matrix with functions in it. And you can imagine that you can still do calculus with these things. You can take derivatives, integrals, things like that. We'll talk about it once we get into the matrix operations section. But again, we can do that. Okay? All right, guys. So there will be a few assignments. You'll notice there's a few assignments from this section, I believe. I'm not sure. But again, this was just here so that you guys know the definitions. Please make sure you actually read the section, right? Because again, it's one thing to hear it from me, but some people would probably like reading it in the book. But of course, you can always look in that section to look up any of the terms that you find that you don't know. Okay? All right. I'll see you guys next class period.